Alright, so this video is going to be covering Chapter 18, Section 3, which deals with the equilibria of acids, bases, and salts. We'll be starting off by looking at the ionization constant of a weak acid. So here we have acetic acid dissolved in water to form hydronium and, a acetic acid ion. And so what you have to realize is that acetic acid, or an acetate ion rather, acetic acid only dissolves 1.3% of its total, basically only 1.3% of the total molecules of acetic acid that go into a solution of water actually dissolve into their component ions. So then realistically, you have to figure that there are three species rather than two that are dissolved in this solution. You have the original acetic acid, you have hydronium, and you have acetate. This means that when you do your equilibria equation, with the products and the reactants, your hydronium and your acetate all over, you have to realize that the reactants are going to play a major role in the actual reaction itself. Because the reactants, this reactant stays in much more so than these products form. Also, what you have to realize is that H2O, despite the fact that it is in fact a reactant in this, dissolving of acetic acid, this H2O is a constant because, if you'll remember, it's a liquid, and pure liquids don't affect the ionization constant, the equilibrium constant. So, instead, we move that up here, we multiply both sides by that KH2O, and because that's a constant, and this is also a constant, we get an abbreviated constant that we'll call Ka for now, which basically stands for the acid ionization constant. Again, this is just an abbreviation version of a standard equilibrium constant, and it's defined just as above, except without the H2O on the bottom. You just have your acetic acid. COOH, like that. Moving on now, we're going to be discussing buffers. And buffers are basically solutions that resist change in pH. So they resist change in pH. And the way they do this is normally through a combination of a weak acid and a salt of that acid. So for example, if we have, once again, acetic acid, which is a weak acid, and you have a salt of that acid, say sodium acetate. So sodium CH3COO, one too many O's, H. And this is a salt of that acid because you can see it has the same ion in it. However, it also has this cation in front. So to realize how this solution will resist change in pH, we have to look at how these break up. So this acetic acid breaks up into its acetate, and then the extra proton it lost forms hydronium, right? Likewise, this will break up into positive sodium and acetic acid. So if you were to add extra hydronium, like say in an acid situation, that would bond to this extra acetate molecule that's floating around and take it out of solution, keeping it neutral. Likewise, if you were to add a strong base and increase the hydroxide concentration, that would neutralize with either the sodium to form sodium hydroxide or with the hydronium itself to form neutral water. So the pH doesn't change if you add tiny amounts of acid or base. Moving on now, we're going to be covering the hydrolysis of salts. And as a basic definition, salts are compounds that form from neutralization reactants. So in the case of the neutralization of hydrochloric acid and sodium hydroxide, the salt is sodium chloride, NaCl, which you should be pretty familiar with at this point as standard table salt. However, when dissolved into solution, this will break up into its constituent cation, that is sodium, and its anion, chlorine. And you'll notice that these two ions, that is the cation, is the cation of its base that initially went into the reaction. Likewise, its anion is the conjugate of the acid that went into the initial neutralization reaction. Now, the reaction of water and this dissolved salt in solution is what is known as hydrolysis. Now, in the case of sodium chloride, which is formed from both a strong acid and strong base, there isn't much hydrolysis that goes on. In other words, these don't interact much with the actual water molecules other than dissolving in solution. But we'll cover more on weak acids and weak bases later. So when you have a cation, like this sodium reacting with water, it's what's known as cation hydrolysis. Likewise, when you have a chlorine ion or some sort of other anion reacting with water, you get what's known as anion hydrolysis. And it's important to note that cation hydrolysis will form an acidic solution, while anion hydrolysis will form a basic solution. So first of the two, we're going to be discussing anion hydrolysis. And here we have a general formula for anion hydrolysis. You have your anion here attached to its proton, and that combines with water in solution to form excess hydronium and the actual anion itself. So that is the anion base with its negative charge. And so from this reaction we get, the equilibrium constant, the acid ionization constant rather, based on the hydronium and the anion concentration themselves in the product side, and the initial acid in the denominator. And basically what happens from here after this reaction takes place is that once you have the anion in solution, that will react with neutral water and basically take on a proton. So this becomes, a Bronson-Lowry base, or acid rather. And it's this second reaction that is responsible for the excess hydroxide that leads to a basic solution during anion hydrolysis. And how basic the solution is, that is, the change in pH and how much is affected, all depends on the strength of this anion as well as its concentration. So, more mathematically, the lower this Ka is, that is, the lower the strength of this anion here, the weaker the acid and the stronger the base. Moving on now to cation hydrolysis, we have a very similar situation in which, the original base interacts with water to form, this positive complex and hydroxide. Now the second reaction is what's really like where the meat and potatoes are. Basically, this basic complex interacts with neutral water to form excess hydronium, leading to an acidic solution. And this is, once again, acidic solutions are the result of cation hydrolysis when you dissolve salts in neutral water. And so the concentration of hydronium, that is how basically what makes, how you measure the pH, all depends on the strength of this complex here, the added BH plus complex. And the lower the Kb, that is, the lower this BH is, then the stronger the donation of protons and therefore a higher concentration of this, basically as a reaction to a decrease in that. So if this is strong, you'll naturally need less of a concentration to get the H3O, and that will lead to a corresponding decrease in the Kb, which indicates an acidic cation hydrolysis process. Now, if you'll recall, when we looked at combining hydrochloric acid and sodium hydroxide to form table salt and water, this neutralization in which the two chemically equivalent amounts occurred during a titration happened at a pH of 7. However, neutralization doesn't always happen at 7. It can happen at 9 or 5, really wherever, depending on the relative strengths of acids and bases that form these salts. So when you dissolve these salts in solution, there's really 4 types of salts you can get. So the 4 types have to do with the constituent acids and bases that initially comprise them. So you can get a strong acid and a strong base, as we have above. You can get a strong acid and a weak base. You can get a weak acid and a strong base, or you can get, a weak acid and a weak base. And that all makes sense. But it should be noted that each of these will have a different effect on the pH of the solution. So basically, the relative strengths of the acids and bases that comprise these salts is what actually is going to determine the pH in the solution. For example, we already know that in strong solutions you get a pH of 7. And that all makes sense because the 2 constituent ions completely ionize and don't really interact with the neutral water all too much. In other words, they don't hydrolyze in solution. However, it's once you get the weak acids and bases involved that things get a bit tricky. So when you have a strong acid and a weak base, you get an acidic solution because only the cations from this acid are going to actually hydrolyze, or rather, only the cations from the base, are going to hydrolyze. Oppositely, if you have a weak acid and a strong base, you're going to get a basic solution because only the anions from the solution are going to hydrolyze, and you're going to end up with a excess negative solution and a higher concentration of hydroxide, basically. Now, when you get into the weak reactions, things get tricky. You can realistically have an acid, a base, or a neutral solution, and this all depends on the relative strengths of the acids and bases involved.